Hey folks, I'm making this video for the AEDD 100 print reading class to make up for the two Zoom videos that did not get recorded in our first two classes. This is the electrical unit, and I'm just going to jump in. First, you need to know that you go to the Google Drive, and on Google Drive there is a folder that you all have a link to that is our common AEDD 100 folder. Open that up. Inside is another folder called AEDD 100 print reading. Open that up, go to the Abbott folder, which is where I'm putting all files that I'll be using for the rest of the semester. In the electrical folder, you'll find a number of different references. One is a PDF of a PowerPoint that I put together on electrical theory. If you've already downloaded this, go and get it again because I've made some substantial changes to it to make it a little more useful to you in this distanced learning environment. I'm going to open up the PDF file that I created from it, and that's where I'm going to start, and I'm going to jump right in. I will say I don't plan to do much editing on this after the fact, so any little glitches or flubs or mistakes I make are going to be in here. So let's just start with the concept here that there's a difference between direct current and alternating current. You've probably all heard that. These two images I have on the opening slide just demonstrates those two differences. The one on the left is known as a direct current system or direct current circuit. On the left, you have the high voltage power lines that would carry electricity to your house. You can't move electricity using direct current over long distances on lines like this. So what you see here on this side, that's all alternating current. Over here on this side, you see what's called direct current. And here's the difference. In both of these circuits, one's called a series, one's called a parallel, we'll get to that in a second. In both of these circuits, you have some kind of force. And that force is generated here by a battery. And the force pushes electrons, which are subatomic particles, over through a wire, which is a good conductor. In this case, through a switch. Now, switches are used all the time to control electricity because in order for electricity to flow, you need a complete circuit from the source back to the source. Open that switch, you have an open circuit, so there's nowhere for electrons to go once it hits here, so there's no movement of electrons. Similar to turning off the water faucet when you have water running in a garden hose. That switch, once it's closed, allows a complete circuit. In this case, a complete circuit called a series circuit, which is very unusual. But in this circuit, and these are incandescent light bulbs, and I'm sure that some of you have, well, you've probably all seen incandescent light bulbs, but another few years of teaching, and I'm going to have to eliminate any reference to incandescent light bulbs because now we use almost exclusively LED lighting because it's so much more energy efficient. A series circuit has current that flows into a device, and when I say device, I mean any device that uses electricity. So you could replace the light bulb here with a toaster or a radio or a TV set or a computer or anything else that uses current for its power, electrical current. In a series circuit, the current, which is all these little electrons, they're just running through this wire. The current has to flow through the device in order to move downstream to the next device. It's not a good system and it's quite inefficient. Then it has to go through that device in order to return back to the battery. When I was a kid, Christmas tree lights were often made this way. Actually, they were all made this way. Great big incandescent bulbs, which generated heat, by the way, which is why so many Christmas tree fires happened when I was a kid. But if the Christmas tree lights went out, my job was to go through with a good bulb, at least one we hoped was a good bulb, unscrew every bulb in the Christmas tree series, and then put the good bulb in until I found the one bulb that had gone bad, and then all the lights would light up again until one of the other bulbs went bad. A parallel circuit, which is how your house is wired, thank God, because otherwise you'd have to have things plugged into every receptacle in order to get current to the next receptacle downstream. They're wired in parallel, and parallel just means instead of going through each device, current goes to each device independently, and then there is a path back to ground from each device, so that once you turn that switch on in this particular circuit, electrons flow through the circuit, through the switch, to that device, and to every other device along the way. So all of the receptacles in your house are wired in parallel, which means you can use any one of them without having the others engaged. Now this is called direct current because in a battery or a fuel cell, that's exactly how the current works. Electrons go out and stay going and moving in the same direction, then return to ground. Over here what we have is power being generated with alternating current. And alternating current means that electrons have to move, and we'll see that in the next slide, but they don't all have to move in the same direction all the time. Alternating current, they literally go back and forth. That movement, though, allows you to use the current flow to do work. The reason why we have alternating current in our households is because direct current cannot be transferred over or transmitted over long distances. Early on, when Edison was developing systems for distributing power, every neighborhood in a city would have to have its own power plant in order to provide electricity to the houses and other buildings nearby, because if they got too far away, it became ridiculously inefficient to try to move current using direct circuits, direct current. Alternating current, it turns out, can be distributed over very long distances with a great deal more efficiency, and that's why nobody in there has a direct current system in their home or their business. Surprisingly, I'm old enough to have worked, when I was 15, I worked for my uncle in a sheet metal fabrication shop in Detroit, Michigan. And we had, one of my first jobs was to take a group of DC wired fans that had been built at a time when the factory that the company that they had was using direct current in Detroit, Michigan. And so these fans were all DC fans. My job was to take them apart and take valuable stuff out of them. Now, we weren't using direct current at the time, but in my lifetime, there were places that used direct current, and that's kind of astonishing to me to look back on it. So AC current, alternating current, that is the kind of current we have now. Now, what is electricity? Electricity is really simple. It's the movement of electrons. You can get electrons, which are subatomic particles, to leave an atom of whatever element they're contained in and move either to the next atom or through air. If you can get that to happen, you have electrical flow. So there are 6 ways that you can get that to happen, and we're going to come back to that in a minute. But just a very brief review that you probably remember of atomic structure. This is an atom, or at least a schematic of an atom. This happens to be an atom of lithium, which is used frequently as an illustration for this process. I should say this concept. But it's used frequently just because it's fairly simple. Lithium has an atomic number of 3. It's an element on the periodic table. We'll look at that briefly. And then on the periodic table, its atomic number is 3, which means it has 3 protons. Well, it has 4 neutrons. Now, neutrons, it's unclear exactly why, in my mind. Different atoms have different numbers of neutrons, but there's something called an atomic mass. And the atomic mass is based on essentially the weight of an entire atom. And depending on the element, the neutrons vary. You don't generally have the same number of neutrons as you do protons, but you always have the same number of electrons as you have protons, because every atom internally is electrically neutral. That means you have the same number of negative particles as you have positive particles, and they have the same mass. Neutrons, on the other hand, are neutral. They have no charge, and so different materials have different numbers of neutrons in ways that are not as obvious as you might think they would be. But you can actually determine that. If you look at a periodic table, there's something called an atomic mass, so you can do a little math and come up with the number of neutrons. The electrons are just, they don't really, my understanding at least, they don't orbit as the way that planets orbit the nucleus. It's just sort of a cloud of electrons out there. And electrons in a cloud form different shells. And so the first shell is the one closest to the neutron, to the nucleus. Then you have other shells, and then you have other shells, and then you have other shells. And that's what differentiates one element from another, is the number of electrons, the number of protons, the number of shells, etc. Now that's the periodic table. I'm sorry, before I leave this, we're going to come back to this, but there are 6 ways you can get electricity by moving electrons. Friction is used to move electrons from one place to another. Pressure, I'll show you what that means in a minute. Electromagnetism, which is the most common way that we have of generating electricity. That's a generator, and the generator, as long as it's turning, can be turned by any number of means. Heat can directly generate electricity. Chemistry can generate electricity, a chemical reaction between various elements. can result in electron flow. And then photovoltaic, so it's a really unusual. In fact, in some ways, it's still the one that's hardest for me to get my head wrapped around. But those are the 6 methods that you have of forcing electrons to move and therefore generating electricity. I will point out, by the way, that no one invented electricity. Some people discovered it over time, but nobody invented it. In fact, we're all electrical. You are a walking bundle of electrical charge and electrical movement. Now, this is the periodic table of the elements. This is every single element. And the periodic table of the elements indicates, if you understand how to read it, how many protons, how many electrons there are. And for people who understand this, you can even determine how many electrons there are in the outer shell, that outer cloud of any given atom. So if you look here, hydrogen, 1 proton, 1 electron. Helium, 2 protons, 2 electrons. Come back down here, lithium, 3 protons, 3 electrons, and on and on and on and on until you get to something like 100 and, what is that, 103. 103 means there's 103 protons and 103 electrons, and many of the things on the periodic table were actually created in labs as opposed to occurring naturally. Now, let's start with the friction as one of the things that causes electricity to flow. It's an interesting process, and you've all encountered it. If you walk across a carpet, your feet are rubbing on the carpet, and all of a sudden you go someplace and touch somebody or touch a doorknob, or even sometimes when I lean over to kiss my wife, the little spark that happens. That little spark is a transfer of electrons from you to whatever they're being attracted to. And this is an interesting concept. It's really the result of friction at the surface of, and mostly insulators. This is coming from carpets and hairs and things that do not by themselves conduct electricity very well. But at the surface of those materials, if you take a microscope and you take something that you think of as quite smooth and you blow it up far enough, you discover that there are all these little bumps all over the surface. So that as you move one surface over another, the more of those bumps, the more friction results. Now, friction results in heat as well, partly because of the movement of electrons. But what will happen apparently, and I've always found this fascinating, is that the electrical movement, the electron movement, is the result of a voltage differential that happens when you squeeze, by friction, the electron cloud around a given atom at the surface. And when you do that, it distorts the structure at the surface in such a way that it produces a voltage difference, and electrons then start to flow. I sort of think of it as you're ripping electrons off of one thing and transferring them to something else. So one place that you see this happening, my buddy Charlie was 5. I was babysitting for him, and just before I went over there, his mother told me when I got there that he asked her what electricity was, and she said, wait till Dan gets here and ask him. So we went and got a balloon, and we spent quite a bit of time with that balloon, rubbing it on his hair and then sticking it on the wall and holding it up so his hair would go up in the air. I took a photo of the balloon on the wall, but the one I took of him with his hair up in the air didn't come out, so I found online this other kid whose hair is sticking up because of static electricity. What's happening here is this. That balloon, when he was rubbing it on his hair, sort of stripped electrons from his hair, transferred them to the balloon. That meant that all these negatively charged electrons were in excess on the surface of the balloon, which means relative to the balloon, the wall had a positive charge. Now, this is an important concept. Positive and negative really have to do with a difference or a voltage differential. So if there's more electrons on that balloon than there are, or there's an excess of electrons on the balloon relative to the wall, which you thought of as neutral before the balloon came near it, is, relative to the balloon, positively charged. We'll get to that in a minute as well, but unlike charges attract each other. So why does that balloon, and I'm sure you've all done this, and if you haven't, you have to go and get a balloon tonight and rub it on your hair. The reason that balloon sticks to the wall is because of the electrical attraction between the highly concentrated number of negatively charged electrons on the balloon relative to the positively charged wall. Eventually, the transfer of all the electrons into the wall will result in the balloon falling off the wall. Here, I'm not exactly sure how this was generated, but when we were doing it, Charlie and I were doing it, we took the balloon and just put it in a big U over his head, and his hair did exactly the same thing. Another place, so balloons and carpets, but the place that is the most powerful electrical force known is lightning. And lightning is also the result of friction. It's the result of friction because during storms there's so much turbulence in the clouds that the water droplets are rubbing up against each other. And those water droplets end up transferring electrons until you get such a heavy load of electrons that they just have to be discharged somewhere. One way is cloud to cloud, which means right here you've got an electrical discharge going from the cloud internally to another part of the cloud, because this part of the cloud, well, I'm not sure exactly which one had it because it's impossible looking at it to know which direction the electrons are flowing. Although it's interesting, the electrons are flowing from the ground to the cloud when you see the current flow, but they're going to the ground and then heavily saturating the ground with electrons prior to that lighting coming on. But anyway, internally from cloud to cloud, it's more negatively charged here than it is here. You get to the point where the electrons just can't help themselves and they go jumping through space and they come over to this part of the cloud. Here, this is a cloud to ground or from ground discharge. And the point I'm going to make here is air is an excellent insulator. It is really hard. You need a lot of force to get electrons to move through the air, which is why the heat generated by lightning, I can't remember exactly, but it's something like 5 or 6 times hotter than the surface of the sun. So this is a tremendously powerful electrical force and more than any other electrical force you could generate. That's friction. There's another way that electricity is generated, and that's with pressure. Something called a piezo crystal, which is a quartz crystal. And a piezo crystal is being used now in 2 places that you might be familiar with. For a while I stopped talking about phonographs because nobody knew what it was, but now phonographs are making a big comeback. So we have phonographs and we have a gas grill lighter. What happens over here, when this person right here pulls that trigger, when that trigger is pulled, it snaps. And if you've ever used one of these, you know that it's a distinct snap. That snap is actually an impact, and that impact hits a piezo crystal and squeezes it. And when you squeeze a piezo crystal, it discharges electrons. In this case, they go through a conductor and then jump across an air gap right here. And as they jump across, they make an arc, which is similar to what happens when you have lightning. Now, over here, you have another piezo crystal. And over here, the piezo crystal, I'm going to use my little drawing thing. Over here, the piezo crystal happens right, didn't do it, did it? Screen draw? I'm trying to do that. Okay, there I go. Right here where the needle is, the piezo crystal is under that needle. And as the needle rides on the grooves of that record, the grooves have valleys and hills essentially. So the needle goes up and down, and as it goes up and down, it squeezes a piezo crystal a little differently. The harder it squeezes it, the more electrons get discharged. The less it squeezes it, the fewer electrons get discharged. And all those electrons then get carried through wires to a preamp and then to an amplifier and get turned into sound, which is sound traced by the pattern formed by the up and down of the electrical charge. So piezo crystal, squeeze it, current comes out. Squeeze it, current comes out, and those tend to be quartz crystals. All right. Movement of electrons again. We're still on movement of electrons. And I think what I'm going to do, let me skip this slide and come back to it. This is the way most of electricity in our homes is generated. So I'm going to come back to this because it's probably the most important one. Just skip down to a thermocouple. So we went through friction, we went through the piezo crystal or pressure. Now we're looking at heat. And this is how electricity can also be generated. What you have here is a schematic of something known as a thermocouple, and over here you see it being used. This is molten steel, talking about 2,000 plus degrees Fahrenheit. And measuring that is something you don't do by dipping your finger in and seeing if it's warm. And you don't do it by dipping any normal thermometer in there either. Anything having to do with glass, for instance, or plastic would just be destroyed. So what you're looking at here is somebody's hand holding onto a handle, and on this side it's over here. You just kind of so he's holding it here. Over here, that's the schematic handle. Now at this end, you have two different metals, and it's represented right here. There's one piece here and one piece here. Those two metals can be a number of different things, but one of the ways that you do this in a science experiment is to have steel and copper. If those are in contact with each other and then they get heated, it causes a transfer of electrons from one to the other. And that transfer of electrons from one to the other, in this case, goes up through these wires and then goes to this plug, which is plugged into a gauge. So at this end, there's a little gauge, and that gauge is affected by the amount of current. So the needle on the gauge goes up or down based on the amount of current flowing, and the hotter that is, the more current. So that needle goes up, the needle goes up, and you can measure the temperature of very, very hot things as a result. Another way is chemical. Now, chemical is obviously with batteries, and batteries. I don't have a schematic of a battery here, but you have a positive and a negative terminal on a battery. You put electricity into a battery, and then you take electricity out until it stops and discharges. And if it's a rechargeable battery, you put the electricity back in, and if it's not, you throw it away. But it is a chemical process, and it requires what's known as an electrolyte, and it requires an anode and a cathode, which is a different way of saying positive and negative. But there are ways of actually creating electricity using chemistry, and one of them, well, the most important one, is a fuel cell. Here's a schematic of a fuel cell over here. The schematic of the fuel cell shows you that you need fuel, and the fuel in this case is hydrogen. And hydrogen coming in and then being affected chemically by being combined with other chemicals. It causes the electrons to be pulled off the hydrogen and to flow up through. This is a resistor, by the way. It's a symbol for resistor. It just means that something up here is using the electricity. Hydrogen ions are essentially electrons that are missing an electron. Atoms that are missing an electron. So they're ionized, and they go flowing through this electrolyte over to this is the anode side, I believe, and that's the cathode side. Oh, it is. It says right there. So the anode side, it goes through this electrolyte to the cathode side, and that's what causes electricity to flow. Interestingly, when oxygen is added to this process, the hydrogen and the oxygen recombine and form water. And so the fuel cell is so attractive as a possible means of generating electricity because the fuel is the most common element on Earth, and the waste product is water. So it's a really benign system, except that it's really hard to scale it up to the point where it's really useful. Now, down here, what I'm showing you is something that is essentially it's an electrical process, but it's essentially a destructive electrical process. Corrosion, whatever that corrosion is, rust in iron or steel, aluminum oxidation, those things are actually electrical phenomena, and this is how it works. Marine use is where I see this most often, but every municipality has like pipes underground, and those pipes underground could essentially start rusting away through this electrical process. The electrical process simply means that in contact with an electrolyte and near something that is more noble, this means it's in a different location on the periodic table, it's possible. If you look up here, let me get my pen out again. This is just a pipeline underground carrying water, probably. And down here you notice it says sacrificial anodes in a tube. There's this electrical connection to these things that are sacrificial, and what it means is that these are made out of an element that is less noble than the element made here, the iron. And as a result, ground becomes an electrolyte if it's moist. Electrical current is going to go from one of these things into the pipe, which means that these sacrificial anodes are going to be losing electrons over time, which means they're essentially disintegrating. But by connecting them to that pipe, it prevents the electrons in the pipe from migrating out of the pipe and disintegrating it in the form of rust. So it's called a sacrificial anode because we're going to sacrifice this less valuable element in order to protect a more valuable element. And down here you have two different materials, and this is a commonly used sacrificial anode. I don't know what they use, to tell you the truth, in the underground pipes, although I assume it's zinc, but it might not be. But in the marine environment, which I'm much more familiar with, you want to avoid this happening to this. This second thing I just circled is the propeller on your boat. In this case, it's made out of bronze. Over here, you've got this thing that's deteriorating that's made out of zinc, and it's specifically placed in contact with the propeller to prevent the propeller from looking like this over time. It's very hard to move a boat if your propeller disintegrates and goes away. So this piece of zinc is attached to the bronze, and it's often used as well with aluminum. That piece of zinc is attached because zinc is less noble, and electrons flow in a current through an electrolyte from the zinc into the bronze. Doesn't hurt the bronze to have an excess of electrons, but it does hurt the zinc to lose them over time because it changes the atomic structure of the zinc, i.e. it basically disintegrates. Now, over here you've got a schematic, and there's zinc and there's copper. And all it is showing you is that electrons are flowing out of the zinc into the copper, and as a result the zinc deteriorates, the copper does not. Now aluminum is the same. Aluminum boats all have to have this. Aluminum components on your engine have to have this. And in fact, I have zincs on the steel components. I have stainless steel trim tabs on my boat, and I put sacrificial anodes on the stainless steel to protect it as well, since it's in salt water, which is a very good electrolyte. In other words, an electrolyte is a substance through which electrons gladly flow. Go to the next slide. Now, before we get back to electromagnetic force, the last one is photovoltaic. This one is just fascinating to me. The way it works, I'm told by people who know more about this than I do, is this. Photons knock electrons free from a solar cell. So what you have over here is sunlight. The sunlight comes down and it hits something that is a material that is a semiconductor material. We'll look at that in a minute as well. What that means is that you've got what's called an N, a PN, and a P-type of material. Negative, positive, negative, kind of together, and positive. And that right there is an image of a photon, which is something in physics that is so baffling to me because it's kind of a thing that actually exists, but it has no mass. And it is what makes up light. And it travels from sunlight in what's called a particle wave fashion. It kind of goes back and forth in a wave, but it also behaves as though it's a particle doing that, except that it has no mass, so it doesn't actually exist. And if you're having trouble imagining that, I don't blame you. I'm having trouble imagining that as well. But somehow those photons of light with the right material, and it doesn't happen obviously with just any material, that's why solar panels are so expensive. If photons hit the right material, they literally knock electrons free and then they start moving. And when you have an electron flow, and they have the electrons flowing out, and then the whole flow is the absence of electrons, i.e. a positive area going in the other direction. Anyway, when you do that, you get an electrical flow, and you put enough of these things together, you have a solar panel. It's amazing to me, the wave particle theory of light. And here's the definition. These photons have no mass at rest and move at 186,000 miles a second, which is the speed of light. Let's go back to electromagnetism. Electromagnetism generates electricity in the most useful possible way for us because it's so easily controlled. You have three elements and you can move electrons. First, you have movement, because you can't move electrons without moving something. What you have to move is a conductor through a magnetic field, or a magnetic field around a conductor, either one. But you need movement, something that will conduct electricity, and a magnetic field. Now, the way that's generated normally, and it doesn't have to be a rotational movement, it can be a linear movement. You could literally say, I'm just going to take and hold a magnet over a piece of wire like that. And if this is a magnet with a positive and a negative, and you move it back and forth, you'll be moving electrons back and forth, and that would be a copper wire. Cu being the, in my clumsy sketching, that would be a copper wire. Copper is a very good conductor. Take any kind of magnet at all, move it back and forth, and electrons are going to be kind of pulled one way or the other momentarily. As soon as you stop moving it, it will stop moving the electrons. But you can actually generate a measurable current by just taking this thing, attaching it to a meter, taking a magnet and moving it back and forth really quickly, and you can see the needle jumping back and forth as it measures the electrical current generated by moving those electrons a little bit. Now, the way to do that efficiently is to spin something. And so that's what a generator is right there. That generator is spinning. It's spinning inside of a magnetic field. The magnetic field is generated by those magnets on the outside. That is what's called a winding. And that winding is shown right over here, right there. So if you take a look at this slide right here, let me see if I can zoom in. Whoop, can I? Thought I could zoom in on it. Well, I can't. So maybe I can. Here we go. Yeah. All right, so I'm going to go to 200%. So right there, those are really, really, really thin wires. I took one apart one time, and miles and miles of extremely thin copper wire. I also tried to build a motor when I was a kid out of this kit that I got, and it involved being too patient for me because I had to sit and wind this thing by hand around an armature. This armature goes inside this case over here. The case is surrounded by magnets on the outside. These wires, by the way, are not being moved through the magnetic field. They're being used just to move the electrons that are being, there's another way, there's an electrical connection between this. That's probably you can see it right there. Those little bars right there, those are actually in physical contact with this as it turns, and so it transfers the electrical current generated within these windings to the outside winding, which is then tapped into something that can be used to actually power something. So as this thing spins up here, all those wires, miles and miles of wires, have electrons moving back and forth, and the longer that winding is, the more current you can generate, and that electricity then comes out of the generator and can be used for something useful. Interestingly enough, this is also the schematic of an electrical motor. If you put electricity into this motor, you can get it to spin inside a magnetic field as well. So if you turn something externally, a generator, turn this externally, it's a generator. If you put electricity into it and cause it to turn from having current coming in, now it's a motor. Now, what can you use to have this thing turn? Well, you can cause this thing to turn in all kinds of ways. The most common is a steam turbine. In other words, you have to heat up water till it turns into steam, force it through a turbine. The turbine then moves. Moving the turbine, it's attached to generators. The generators then move. As the generators spin, and by the way, generators can be tiny, tiny, tiny things. Maybe some of you have had one on your bicycle before. Well, they can be so large that if you pulled the armature out, the whole class could go and sit inside of the case. And that's the case at large power plants. So as long as you can turn that, you can create electricity. And so you create steam to turn it. Well, how do you make steam? You heat up water. How do you heat up water? Natural gas, oil, wood can be used for that purpose. Nuclear fusion can be used for that purpose. Fission can be used for that purpose. Any of those is going to work as long as you can produce steam from them. Hydropower can also be used to turn it. You can put a generator in a river and let the current flow over it. You can have tidal current in the ocean where the tide comes in, the tide goes out. They've had generators attached to the seafloor that allow the tidal current going in and out to turn them. Just the wave action from the ocean with the wind blowing back and forth and causing waves, That alone can be used to generate current, and all of those techniques have been used. In fact, a great deal of our power in Maine comes from hydropower, and that project that CMP is planning on putting in where the transmission line goes through the state of Maine, that's all going to be hydropower. In that case, dammed up rivers that are then used to turn those generators. I will make a point about that. It's not quite as obvious as you might think that we, of course, should be using hydropower to generate electricity, because in order to have a constant flow of hydropower, you don't just stick a generator in a river, you actually dam the river, create a fairly large pool, sometimes a really large pool, a lake essentially, which of course has its own environmental problems. And that then is held back with a dam, and it's the dam's discharge that's used to turn the generator to make the power. But the other is wind, and wind is being used more and more often, and it's becoming more and more efficient. I grew up in Rumford, Maine, and I go up there now on the way home, and I see windmills along the ridges up there all over the place, including in a town I once lived in called Byron. The other thing that's happening in Maine is they're testing the feasibility of putting wind generating stations out in the ocean. But again, there's some balance, some balances here, or trade-offs. When you put things in the ocean, it has an effect on the ocean. And if your job is catching fish and you're out there trying to do it, and there's something that showed up that disrupts the process of you doing that, that's a downside. So there is no magic cure to how we generate the electricity we use. Um, but there's no question electricity is the most important form of energy that we use on a regular basis. And, as most of you know, I have a fully electric car and a plug-in hybrid car, and I've been interested for actually decades in alternative energy, in particular the use of electricity, because I think it's probably easier to manage electrical development or the electrical generation at one plant than it is to fill a bunch of cars with gasoline and have them drive around. Whatever fuel gets used to generate the electricity can become cleaner and cleaner if it's concentrated and people do use enough mitigation factors. But none of this is easy. There's no one obvious solution to any of the problems we face with electricity. Now we're moving to the law of charges. And where we're going eventually with this is I'm going to have you do a circuit diagram. I'm going to have you attempt a circuit diagram. A circuit diagram is something probably you're not going to get completely right unless you're an electrical major and an electrician. But I will have you do a switching diagram, and that switching diagram is going to be based on the National Electrical Code, which controls or manages the installation of electrical systems in the United States. The National Electrical Code has been adopted by virtually every state. I'm going to say every state. I don't know that for sure, but probably every state. And that's what electricians have to follow when they do wiring. So we're going to go through the National Electrical Code requirements for residential, and then I'm going to have you do a switching diagram. I'm going to have you do a circuit diagram, and I'm going to have you do a load calculation on a specific house to determine what the maximum load is for the residents. So before we get there, though, still in the topic of electrical theory, one of the things you need to keep in mind, and this you probably know, is this idea of the law of charges, that opposites attract, which means that like charges repulse. So you've got these things hanging here. Think of those as protons and those as electrons, and those as protons and those as neutrons. If there are two electrons hanging beside each other, they're going to push each other away. If there are two protons beside each other, they're going to push each other away. If there are two neutrons hanging beside each other, nothing's going to happen. They're neutrally charged. They have no effect on each other. If you have unlike charges, negative and positive hanging together, they're going to want to go and join. So like charges repel, unlike charges attract. There is a difference between classical electrical theory and actual electrical theory. Thomas Edison, long before. Benjamin Franklin postulated that electricity flowed. So the whole thing with Benjamin Franklin and the kites, it's more or less true, although well, more or less. In the sense that he did theorize that electricity was a concept, it was something real that moved from one place to another, and he felt that that was pretty obvious from lightning. He actually even came up with this notion of negative and charge and positive. And what he theorized is that the electrons flowed from a positive to a negative charge. Well, he had no way of being able to check that because at 186,000 miles a second, it's really impossible for Ben Franklin to take out his whatever. He would have had to measure time then, which might have been a watch. Would it have been? Yeah, I guess it could have been. Or whatever. At any rate, in reality, we now know, or scientists now know, that electrons actually go from negative to positive. So it's interesting though, because in physics, I believe they still use classical electrical theory when they're talking about electron flow, whereas in reality, with electrical engineers and people dealing with electronics, they actually consider it to go in the direction it actually does. It makes no difference as far as any of the math goes. So there's no difference between physics theory and electronics theory as far as doing all the math. It's just conceptually, in one case they think electrons go positive to negative, and the other they think electrons go negative to positive. So here's the key thing right here. This is the key thing you have to understand in order to understand why some things are conductors and why some things aren't. A conductor is an element, or an alloy, but it contains elements, that has some free electrons in its outer shell. So the outer shell of an atom is fully populated with electrons if it has 8. If there are fewer than 4 electrons in the outer shell, they are not bound as tightly to the atom as if there were more than that. So, you and a group of your friends are walking down the street and you're in a tight pack, and then one of you is kind of lagging behind, or maybe think of it in terms of a herd of antelope, and there's one antelope that's not in the pack. It's a lot easier for a predator to get that one antelope and remove it from the pack than it is if the antelope was surrounded by other antelopes. The point is that the fewer electrons there are in the outer shell, the more likely it is that you can get that electron to move from one atom to another, and if you do that, you've got electrical flow. So any conductor has to have fewer than 4 electrons in the outer shell. Copper is an excellent conductor. Why? It has 1 free electron in the outer shell. All good conductors have 1, 2 sometimes, but really good conductors have 1. An electron from an adjacent atom repels the lone attractant electron in the outer shell. So if you got these two atoms together and you push on one electron just a little bit somehow with one of those 6 methods I mentioned, it's very easy to knock one electron free from one atom and have it move to the next atom, at which point it repels the electron that's already there, which gets knocked away and moves to the next atom. And you get enough of these billions and billions and billions of atoms doing that and all these electrons, you have electron flow, and that's what current is. An insulator has anywhere from 5 to 8 electrons in the outer shell. That's a full complement, is 8. So it's harder to break them apart. So things that do not act as good conductors, things like plastics and glass, etc., are composed of molecules that have atoms in them where the atoms themselves are tightly bound to their electrons in such a way that it's hard to get current to flow because it's hard to get electrons to leave. Then there's this really special category, just a few elements that are called semiconductors that have 4 electrons. In other words, they're not conductors because it's not less than 4. They're not insulators because it's not more than 4. So they are semiconductors. And by doing a little magic, people in a lab can set these up so they're either P, N, or PN charged. In other words, you can take a semiconductor, and by manipulating it in a laboratory, you can either make it be a little bit of a conductor or a little bit of an insulator. And what that means is you can use semiconductors as switches that can go on and off. And then you have computer systems and you have electrical circuits, electronic circuits. All right, now, a few other things on the fundamentals. Relative conductivities. Over here I have a list of metals and how conductive they are. And you'll notice there's a reason why copper is used in your home. Silver would be a slightly better conductor. So, if you really, really wanted to be the top conductor dog on your street, you would replace all your copper wire with silver wire. Because if you notice here, the relative electrical conductivity at 20 degrees centigrade is a whopping 6% higher than copper. If you look though, gold, which is a pretty good conductor, is much worse than copper relative to silver. Aluminum, which we use in wires all the time, is even lower. It's only 62% as conductive at that temperature. Why don't we use silver? It's pretty obvious. Silver is rare. It's expensive. You don't want silver wires in your house because it will give you no benefit. Why do we use copper? Because it is relatively inexpensive, relatively common, and a very good conductor. Why don't we use gold? Well, it's not as good a conductor and it's wicked expensive. Why do we use aluminum? Well, on occasion we use aluminum because it is much cheaper than copper. And even though it's not a great conductor, it's a good enough conductor for really large voltage loads, for large amounts of current being pushed with large amounts of voltage. It's just far, far, far less expensive to move electricity from a power plant to your house using aluminum wire than it is using copper wire. And as a result, it's worth it to use aluminum. Now, why don't we just use aluminum in your home, in the walls? Because of that problem of corrosion that we talked about earlier. That aluminum wire was used, in fact, in homes directly after World War II quite frequently because World War II used and generated so much aluminum that when the war ended, there was a massive amount of surplus aluminum. And there were two things that were done with that aluminum. One was, let's put it in wires and make our houses wired with aluminum. And the other was, let's make boats out of aluminum because, boy, it's lighter and wouldn't that be cool? We could use up all this aluminum and it would be great. There were two problems with that. One is the aluminum wiring in houses, where it was connected to a device with a screw that was made out of a different metal, would tend to corrode to the point where it would then lose its good contact, and that contact would become loose, and the loose contact would cause arcing, and the arcing would burn down the houses, which is why you don't find any houses now with aluminum wiring. They either burned down or somebody went, oh my God, I'm getting rid of that aluminum wiring because my friends' houses are all burning down. Boats, however, instead of just saying, okay, we're not going to make boats out of aluminum, they discovered that if you put a sacrificial anode, like zinc, on a boat, you could protect the aluminum, which is why every aluminum boat has some kind of sacrificial anode that would keep it from corroding in salt water. I had an aluminum boat once. I loved that boat. I had anodes everywhere. And I discovered one time that I had water coming into the boat. And when I took it home and put a little water in the bottom to see what happened, it had, well, I didn't count them, but probably 60 or 70 tiny leaks in the bottom of the boat. When I pulled the deck of the boat to see what was going on, this is a riveted aluminum boat, not welded. Somebody had done some electrical wiring at some point before I bought it, and they just cut all the wire and they just left the little strands of copper in the bottom of the boat. And over time, those little strands of copper had settled to the bottom, and the ones that got caught near a rivet caused corrosion around the head of the rivet to the point where it was leaking, even though on the outside of the boat it looked really sound. I had so many leaks in that boat, but they were so tiny that most of the time it didn't matter. But I discovered it one time when I was just sitting for several hours, just, anchored, reading, and all of a sudden I realized the back end of my boat was a little lower than I thought it should be. So, there's the relative conductivities. As far as atomic structure goes, if you look at the difference between insulators, semiconductors, and conductors, here's the atomic structure of a conductor. 1 to 3 valence electrons, just this means the ones in the outer shell. You have one electron sticking out here, you can just see it's completely unprotected by, at least it's completely unbound by all these other electrons. Very easy to knock that free, and if you knock that free from one atom and it goes to the next atom, you have electrical flow. Insulator over here, full valence shell. Now they're only showing 6 here because this particular atom that they selected, 6 is the total load in the outer shell. I think they should have put 8 in there because that's what's true in most cases. I didn't notice that when I found this image. But then a semiconductor has 4, which means if you can get one to go away, you have a conductor. If you get another one to join it, you have an insulator. This is copper. And copper is really good because it has that one electron in the outer shell. And semiconductors, the semiconductors that have four electrons in the outer shell. Carbon's one. Carbon, for reasons I don't understand, isn't really used in the semiconductor industry, but silicon and germanium are. Silicon is being the most common. So you have conductors, semiconductors, and over here you have insulators. Now, the best possible insulator is one that has a fully stocked or fully populated outer shell. These are actually semiconductors as well. But if you look over here, these are the noble gases in the periodic table. All of these have 8 electrons in their outer shell. Helium, neon, argon, krypton, xenon, radon, and I don't even know what this thing is. Oh, well, since they don't know what the mass is, I guess they don't either. That's one of the generated in a laboratory elements. The ones up here that are useful to us are helium, neon, argon, krypton to some extent, and xenon to some extent, I guess. But what we use these for in industry, in the industries that we're most involved with, well, neon, used in neon signs. But let's just talk helium and argon. Those are the two most interesting from my point of view from the industries that I've worked in. The helium and argon are both used because they're noble gases with 8 electrons in the outer shell. They're called inert gases. They're both used in welding to protect welds from having impurities in the air combined with the weld at high temperatures and chemically changing the surface of the weld into things that have defects. So heliarc welding is a helium gas process of protecting a weld. Argon is often used instead of helium, and oftentimes a combination of carbon dioxide and argon, or carbon dioxide and helium, are used. I want to say one thing about helium. The reason why people are able to breathe helium out of helium balloons, which is lighter than air, which is why we have helium balloons. But I've known of people who do this, and if you've ever had somebody do it, you might have been just amused by the fact that they sound like Minnie Mouse. They sound like Minnie Mouse because if you breathe helium and then talk while it breathes out, helium is so much less dense than air that your vocal cords are able to vibrate up and down much, 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 much further than they are in air. And as a result, the pitch or frequency of your voice goes up as the distance your vocal cords vibrate goes up. The problem with that is that helium won't kill you because it's an inert gas. You can breathe it all day long. Unless it prevents you from getting enough oxygen, it's not going to have any detrimental effect on you directly. But there have been many, many cases of people getting drunk and being amused by breathing helium balloons over and over again, whose vocal cords as a result have stretched so far that they're permanently damaged, in which case you don't sound like much after that. So that momentary ability to make your friends laugh because you sound like Minnie Mouse could have a big price to pay, i.e. don't do it. That's my Uncle Dan moment for today. Now, go on to the next thing. I've got about 8 minutes before it's an hour, so what I want to do is to finish up with this notion of electrical flow, because I want to end up talking briefly about Ohm's law and the power formula that we'll come back to. There is an analogy used frequently for electrical flow called the water analogy. The water analogy works really, really well from my point of view in helping people understand the relationship between voltage, current, and resistance. So if you look up here, this is a water system. And what I've got here is constant pressure. So let's say you had a manifold on your garden hose that allowed you to attach 3 separate garden hoses. Coming into that manifold, there's constant pressure, and we'll say you have an unlimited source because there's plenty of water when you turn the big faucet on. Now these are individual hoses, and we could have a 4th hose up here that had a nozzle that was completely closed, so there would be no flow going through that one. Here you have a very small opening, and so you have the same pressure and the same amount of water available, but the flow of water is very small because it's going through such a tiny opening. The resistance of that opening is such that it reduces the current flow to something pretty small. You come down here, you open up that orifice or the nozzle on your hose a little more. Now you've reduced the resistance. As a result, it's much easier for water to flow through. Same force, more water because there's lower resistance. You come down here and you're wide open. You take that nozzle, you open it wide open, and you just got water gushing out of that thing. And the water gushing out of that thing is more powerful. I mean, has more water. You can use it to wash your car, etc., etc. The only difference is that's the lowest possible resistance. So the relationship here between the amount of pressure and the amount of current that flows through, that relationship is controlled by the amount of resistance. So if we were to increase the pressure, we would increase the current no matter what we did with the nozzle. If we were to change the resistance by adjusting the nozzle, it's going to change the current flow. Either one of those things is going to have an effect on current, and there's a mathematical relationship that you can then transfer to electricity that works really well, and it's called Ohm's law. There's also something called a power formula. So let's take a look at the relationship here. Water pressure in electrical terms is voltage, and down here the electronics water analogy, voltage is like water pressure. It's actually called Electro-Motive Force, technically. The letter E is used to represent voltage, and V is used to represent the units that measure voltage. So electromotive force is how much pressure is there pushing on electrons to get them to move, equivalent to water pressure. Current is the rate at which the water flows, and it's also the rate at which the electrical current flows. So if you look at here, current right here, current is like water flowing through a pipe. So the amount of water flowing through the pipe, the amount of electrons flowing through, very similar. And by the way, like water, if you have a really, really tiny wire, you can't get a whole lot of flow. If you have a really, really, really tiny hose here, you don't get a whole lot of flow. The bigger the wire, the more current can go through it. The smaller the wire, the less current can go through it, just like there would be with your garden hose. And then resistance is the size of the pipe or the hose or the position of the valve. In other words, how much resistance to current flow is applied by whatever device is used to control it. So it says resistance is related to the diameter of the pipe. Water pushed through a pipe can do work. Electrons pushed through a wire can do work. Now, work means the combination of how much pressure and how much current determines how much work can be done. So you come over here to this water wheel thing. And the water wheel thing means if you increase the current flow over that water wheel, it's going to work harder. If you increase the pressure that pushes the current over there, it's also going to work harder. Sort of like sometimes you increase the pressure on something and you can wash the dirt off your car better. The combination of the amount of water pressure and the current flow determines how much work you can get out of that water wheel. That brings us to Ohm's law. Now, I often, when I'm teaching, go from this to this, and people kind of take a deep breath and go, okay, I'm going to stop paying attention. And I'm going to tell you right now, do not stop paying attention. I know that some of you think you can't do math, and I believe I have proved that that is not true. Some of you struggle more than others, but you can all do math. And the one thing I can guarantee is you all understand and have the logic necessary to understand what we're looking at right here. Math could not get simpler than Ohm's law and the power formula. Back here, if everything I said here made sense to you, then you understand this. This is simply a mathematical way of representing a real relationship, and that real relationship is among those three things: force, current, resistance. Now, E in this formula, it's just something equals something times something. 100 equals 2 times 50. You know that. Well, 100 in this case is the electromotive force. The 2 is the resistance and the 50 is the current. But those are just numbers, and you just multiply the two numbers on this side and you get the number on that side. The power formula we'll get to in a minute. This is a relationship between or among voltage, current, and resistance. Voltage, well, electromotive force, that's why it's the letter E, measured in volts, is equal to current, inductive current, which is why it's the letter I, measured in amps, times the resistance measured in ohms. Ohms are just a unit of measure that's named after the person who came up with this formula, and it's because we didn't have any other good way of measuring it. So ohms, and it's represented by the omega, the Greek letter omega. Well, if you look at this, let's just see if this holds. What would happen to the current flow up here? If I didn't do anything to the resistance, if I left it set to medium, what would happen to the flow if I increase the amount of pressure? I'd get more water. Make that number bigger, keep that number the same. The only way for that equation to be true is for that number to get bigger. Increase force, maintain resistance at the same level, current goes up. Now, what happens if this number stays the same and this number goes up? What happens to that number to make an equality? The more resistance, the smaller that number has to be. The more resistance in this system right here, the smaller the amount of current. Oh, I got my 1 hour mark here. So, all right, so just 2 more slides and then I'm going to move to the next thing. Next thing is this. It's obviously a different concept altogether, but I'm going to finish up the electrical theory part of this. So that's Ohm's law, simply applied Ohm's law, and it's really, really useful, especially when combined with the power formula, for you to make some decisions about why can't I plug my toaster oven, my toaster, and my dishwasher in the same circuit at my house without blowing a fuse. It's because of the combination of Ohm's law and the power formula. And it's actually very easy for you to make a decision about how many appliances you can put on one circuit if you understand these formulas. And the math of them could not be easier. I mean, I say, what's your salary? Used to be $100 a week. I'm going to double it. What is it now? $200 a week. If that makes sense to you, if you understand that, you understand the math. Electromotive force equals inductive current times resistance. Now, there's a little mnemonic device that I've always used when I first learned this. And I always learned this by drawing a circle, putting a line through it here, putting a line through it here, and putting an E, an I, and an R. Electromotive force measured in volts, inductive current measured in amps, resistance measured in ohms. And we'll get to the other one here, which is the power formula. Power measured in watts is the combination of current and volt. The more current and more pressure you have, the more power you have, the more work you can do in a system. Now, P for power, I for inductive current, E for volts. So this is how I remembered it. I look in the sky and see an eagle hovering over a poor defenseless rabbit as I eat my PIE. Laugh if you will, but it got me through a lot of exams. I see an eagle soaring over a rabbit as I eat my pie. And all these formulas right here are simply math formulas that are generated from this one. If E equals I times R, what is I equal to? E divided by R. What is R equal to? E divided by I. If power is current times voltage, current must be power divided by voltage. And then you can put them all together and you end up with that. Don't panic on that one. I'm not going to make you memorize that. I don't find that useful as a mnemonic device, but it's useful as a way of indicating that if you know these two formulas, you can do most of the calculations. We can do all the calculations necessary for what we're going to do in this class. Now I'm going to stop this video. This is the electrical theory part. I'm going to post it and I'll send you a link. And I'm going to go on and make another video on the other things we've covered.